So far in the previous chapter, we've talked about bonding, and that's called the Lewis theory. And in the Lewis theory, you just deal with the valence electrons, and we talk about how those electrons are given or taken or shared. And in the sharing, you learn about how they're equally shared or unequally shared depending on electronegativity of elements. So now we'll talk about two more theories of bonding. So the first theory that we will talk about in this different theories is the valence bond theory. The valence bond theory has to do with the quantum chemistry, and quantum chemistry, as you know, involves orbitals, the SPDF. So we say that when we have orbitals, that's the region where electrons can be found, and those orbitals then will occupy the same region. When they're occupying the same region, then there is an overlap, and when there's an overlap, there is a bond. Usually in that overlap, you will have only two electrons. If there are more orbitals, then you can have more electrons. But in one orbital overlap, you can only have two electrons. The better the orbital overlap, the stronger the bond. The more electrons that are overlapping, the stronger the bond. Okay, and so we have to keep account of how many electrons are being shared. Okay, so as we talked about in the Lewis theory also, that you have single bond, double bond, triple bond. That's what we are talking about over here. And then finally, in the last portion, we also talk a little bit about the shapes of these orbitals. So S orbitals are very simple. They're spherically shaped, but as you get into the P, D, and F, then the shape gets more and more complex. And so these bonds then will have very specific directions. So let's take an example of methane. It's a very nice molecule, small one to start with. It is CH4, where carbon is the central atom, and carbon has the electronic configuration of 1s2, 2s2, 2p2, because it has 6 electrons. The valence electrons that we have are, of course, the second shell, which is the 2s2 and 2p2. So which means that our bonding electrons are going to be in the S subshell and the p subshell. The S is spherical and p is dumbbell orbital. Okay, and so that's what the valence electrons are going to look like. The hydrogen is pretty simple because hydrogen is 1s1, which means all the electrons are in a spherical shape, okay, or they occupy a spherical region. So that's what these orbitals over here mean, okay, for us in the structure that you see on the right side. So we have carbon in the center, where we have the white over here. These two are the S electrons, and the dumbbell shapes, of course, these are the p electrons, and we have two of those. The hydrogen is spherical, and so all the hydrogens here that I've shown to you, these are all spherical. Now looking at the structure according to orbital theory, it doesn't quite look right, okay, because you have the hydrogens here overlapping with S orbital, but here it is with p orbital. So which means that, first of all, these two, the S overlap, they look a little shorter. The S and the p overlap, they look a little bit longer, which also means that the SS bond may appear to be a little bit stronger than the S and p overlap. So it means that we have two different kinds of bonds, but really that does not happen. Okay, and so what we have is 4 equal bonds between carbon and hydrogen. So if there are 4 equal bonds, which means they have the 4 of the same bond length and the bond energy, then what is going on? There has to be something else, because obviously this theory, the Lewis theory, is not explaining how all these bonds are equal. Okay, and that's where the valence bond theory comes in. So what valence bond theory is saying is that there is hybridization going on, and hybridization meaning that you are mixing orbitals, okay, together. So you can now mix any kinds of orbitals together, the S, P, or D, and in some cases F, okay, but we are not going to be dealing with F so much. So SPD orbitals, you can mix those, and once you mix those, you get a whole set of new orbitals which then look alike. Okay, so for example, you can take one S orbital and one P orbital, and so if you're mixing one S and one P, that will give rise to two sp orbitals. Okay, so when you mix these two, you don't just get one orbital. Whatever number of orbitals you mix, you get that number of orbitals. So if you mix two orbitals, you end up getting two orbitals that are equal. Okay, so if you have one s and two p, then you get three sp2 orbitals. So sp2 meaning one s orbital and two of the p orbitals. One s orbital and 3 p orbitals gives the 4 sp3 orbitals. Okay, so which means we have sp3, 1s, and 3 p orbitals combining. And just by looking at this sp3, you can see that there are actually 4 orbitals being combined over here, and that's why there is the number 4. Okay, you have 4 orbitals forming. So you can have s, p, and d also giving you 5 orbitals, and then s, p, and d orbitals giving you also 6. Okay, so 1 plus 3 plus 2. Okay, so you have now 6 orbitals. This kind of a mixing is called hybridization. And once we do hybridization, then you get orbitals of equal energy, equal size, equal shape, everything is equal. And that's what hybrid means. Okay, it means that taking something that are two different things and then blending them in such a way that you really cannot tell them apart anymore. Okay, and both of them behave exactly the same way. So whether you're forming 2 of the sp or 3 of the sp2, it doesn't matter. Even in the case of 6 sp3d2 orbitals, all the 6 will be alike. Okay, and that is the key of hybridization. So we're going to take the first 3 of them one by one and then try to understand what this hybridization is and how it occurs. One thing to keep in mind before I go on is that hybridization is a key thing only for valence electrons, and it's used only for bonding. If something is not bonding, for example, the core electrons, then they are not hybridized. Okay, and so only the electrons that will be bonding usually will be hybridized, and whatever valence electrons you will find will also hybridize. Okay, so sometimes the lone pair of electrons that we have left over, they will also be hybridized because they are found in the valence shell. Okay, the D is the exception, as we know that from before also, because D is in core, but in some cases you do have bonding with D. So let's start looking at beryllium chloride, BeCl2, and we will start with the sp hybridization for this one. Okay, and so this is what the structure is according to the VSEPR theory, which is what we've done before, the Vesper theory. And beryllium is in the middle, and you have chlorine on either side. Okay, and as we know from VSEPR also is that this is a linear molecule. Okay, and so this is what it looks like. This is the ground state electronic configuration of beryllium, and you will note that this is only for the valence electrons. Okay, we're not taking the core electrons because core electrons don't bond. So beryllium is 2s2, 2p, there's nothing in here. Okay, and so what happens then is the excited state during bonding when electrons start jumping around. And so in the excited state of beryllium, one electron will jump from the s orbital to the p orbital. Okay, and it can jump in the p orbital only because it is empty. If it was not empty, then there'll be no space for it to go. So this is empty over here, so one electron jumps from s to p. Now what happens is the hybridization, okay, where these two electrons, the one of the s and one of the p, will hybridize. Okay, now this hybridization could not have taken place if there was ground state. Okay, because in the ground state both the electrons were in the s orbital. Okay, but now the hybridization has to take place because one electron jumped from the s to the p, and we don't have to question about the jumping part because it is going to jump. Okay, when bonding occurs, then the electrons will occupy all the orbitals singly as possible. Okay, and that is because now they have high energy. So here we have the one electron in the s and one electron in the p. The electron is not so important. Well, it is important, but what is also more important is the orbital that is mixing, okay? Because we have the s orbital and the p orbital that are mixing. So it gives you the two sp orbitals now because you have the one of the s and one of the p. So two sp orbitals, okay? And then you have the two p orbitals that are actually left behind, okay? Those are not hybridized. So this is what the central atom will look like. This is what it was initially. Where we had the unhybridized electrons, and now we have the hybridized, and you can see the green one now. Okay, look at the shape of it. Okay, it is slightly different. So in this shape you have a slightly spherical look to it. Okay, the purple one was the initial p orbital, And now this is the new p orbital, okay? And this is the hybridized orbital now, and the s is mixed in it, and that's why you don't see the s anymore. These transparent one or the white ones, these are still the unhybridized p orbitals, which are still existing. They're there, they're just not hybridized, okay? Because there was nothing in it to mix. If there was electrons in it to mix, it will mix, okay? But there were no electrons, so there was nothing to mix, all right? So here is the new orbital with slightly a different shape. So then this is what we have now as our new bonding system, okay, where we have the chlorine atoms, the BeCl2 that we are trying to make. So here we have the two chlorine atoms, and this is what the electronic configuration of chlorine is. And again, this is only the valence shell, not the core. And here's the beryllium. The beryllium now is the sp hybridized, okay, so it is not the original 2s2, it is now sp hybridized, all right. And so this is what the bonding is going to look like, where you have the beryllium. This is the hybridized orbital, the green one, and the chlorine comes in. Now the chlorine is not hybridized, and usually you will see that the terminal atoms are not going to be hybridized. It's only the central atom that is hybridized, all right? So the terminal atoms, whether it is hydrogen or chlorine or oxygen, they will never be hybridized, okay? It's only the central atom that you got to focus on. So here we have chlorine with the p orbitals, and here we have beryllium, and the green is the hybridized orbitals, and that's where the overlap takes place. Now, according to the VSEPR theory, as we talked about, that it has to be, the electrons are going to be as far away from each other as possible. That is still true, okay? And so the bond angle here is still going to be 180 degree, and that is a characteristic of sp hybridization as well. Now let's look at the sp2 hybridization example, and the classic molecule to take here is BF3, and this is the structure that we drew out for BF3 when we were learning about Lewis structures, where you put boron in the middle and fluorine is all the terminal atoms, and this is what the structure came out to be, and according to VSEPR we called it trigonal planar, okay? And so let's look at the hybridization for this one. Boron is the central atom again. Terminal atoms don't mind, okay? And so we don't do hybridization for terminal atoms. So the boron is the central atom, and 2s2, 2p1 is the valence electronic configuration, okay? So which means the valence shell only, again, not looking at core. Once boron is excited, okay, during bonding, then we have one electron jumping from the s to the p orbital, and now you have 3 electrons that are equally distributed. So then we have one of the s orbital and 2 of the p orbitals that will mix together. Now in the previous case we only had the s and the p because the other p was empty, but now actually we have an electron in here, so we can mix these 2 p orbitals. So sp2 orbitals that are mixing together, so which means if you're mixing 3 orbitals, you will get 3 mixed orbitals at the end, or 3 hybridized orbitals at the end. And the hybridization here is called sp2 because you're mixing 1 s and 2 p. The one of the p orbitals is still left behind, okay, because that did not hybridize because it didn't have any electrons in there. So if you look at the figure over here, you will see that the white one or the transparent one is the original p, which did not hybridize, and the green one is now the hybridized orbitals. And again, it doesn't exactly look like the p dumbbell because now it has some s character in it. So it is about 33% s character. And so it's a slightly different shape, okay? But the nice thing about the hybridization is that all these 3 orbitals look exactly the same, okay? Unlike what we had before, where if you had 2 of the s2 electrons, which would be spherical, and 1 of them would be dumbbell. But now the 3 orbitals which are hybridized look exactly the same. So then this is what the structure would look like, all right? We are now going to take fluorine, and fluorine is the valence electronic configuration of fluorine is 2s2, 2p5, and then we have the boron with the new hybridized orbitals with the sp2. The p is still there again, it's just not occupied, but it's still there, Okay, and so you take these hybridized orbitals, and this is what the bonding would look like then, where you have the boron in the middle and the fluorine trying to share electrons, and the final structure is like this. The bond angle did not change. According to VSEPR, the bond angle was 120, and the bond angle is still 120. The shape is still trigonal planar. Okay, so those things have not changed. The only thing we have changed during all this bonding is how these orbitals actually look like, all right? Because the Lewis theory does not explain what these orbitals look like. So valence bond theory really helps us to understand how these bonds are all the same, okay, how they're all equal. So this is what BF3 looks like, and this is sp2 hybridization. Now for sp3 hybridization, we'll go to our favorite molecule, which is methane, which is how we got started. So for methane molecule, this is what we drew out first. Okay, so we have carbon and the 4 hydrogens on the side, and we talked about the shape of the molecule, and we said it is tetrahedral, okay, according to the Vesper theory, and that is all fine, all right? So now we'll take carbon and take the valence electrons, which is 2s2, 2p2, and then in the excited state, what we will have is one electron from the s jumping to the empty orbital over here, okay, for the p. Once that happens, this is what you end up getting, one electron each in all the orbitals. Now, since all of these orbitals are occupied, all of them are going to hybridize. So which means you have S and 3p, and hence sp3 hybridization. So here we took something that was lower energy, high energy, mixed them up and got 4 orbitals that are now completely equal in energy. So this is what the hybridization would look like. We have the S and the 3 of the p mixing together, and now everything is mixed and you get 4 new orbitals. Okay, so if you want to think about it in another way, you can think about these s and p electrons as clouds, because remember, you can't find an electron specifically. So if these are all clouds, have them all merge in your mind and then separate them out into 4 equal orbitals. Okay, and so this is what the 4 equal orbitals would look like, where all of them are exactly the same shape, size, energy, everything is the same, hence the word hybridization. So anyhow, this is what it looks like, okay, where you have the 4 orbitals. And now for the bonding. So here we have the four hydrogens, which is 1s1, and the carbon, which are the sp3. There are no vacant p orbitals left now because all of them are occupied. And this gives us CH4, and this is what the bonding would look like eventually then, okay, where you have carbon in the middle, 4 equal hybridized orbitals, and the 4 hydrogens coming together, and here's the bonding. The bond angle is still 109.5, the shape is still tetrahedral, but now our structure looks a lot more decent than what it did before, where we had 2 equal and 2 of the unequal bonds in there. Okay, and so that is the advantage of hybridization, is that we can see how these orbitals can look alike and how these bonds have the same energy and bond length and all that good stuff. So that's what hybridization is. Now, one of the things about hybridization that I would like to mention to you before I go on is that hybridization is a theory, and it's quite proven, okay, in the sense that we know there must be something going on, otherwise the bond lengths and the bond energy would be different, but they're not. Okay, so we know that hybridization does occur. Now let's see how you can work out a hybridization, because how do you look at a molecule and determine what the hybridization is going to be on that central atom? Now remember, it's only the central atoms that are being hybridized, not the terminal. Okay, so how do you figure that out? Okay, so here's your guideline. The first thing you do for working on hybridization is write the Lewis structure. If your Lewis structure is not correct, your answer will not be correct either. Okay, and so write out the Lewis structure, the correct one, including all the lone pair of electrons. Do not forget any electron at all. Again, the terminal atoms don't matter, okay? It's only the central atoms that will determine your hybridization, but you still should write all the electrons out. Use the VSEPR theory to determine the electron geometry. Okay, remember the electron geometry for us is the AX formula. Okay, because that gives you the total number of electrons that are going to be around. I'm not talking about the shape of the molecule. Okay, there are two different things. So I'm talking about electronic geometry, all right, which is how many electron groups do you have around the central atom. From the electronic geometry, then now you can figure out what the hybridization will be. Okay, so then you assign the valence electrons to the hybrid orbitals, and then you can write out the hybridized structure. Okay, it's as simple as that, but you have to start with the Lewis structure and you have to have the right Lewis structure. So this is what it is like: Lewis structure, number of electron domains, or the electron geometry, which again is also the Axe formula, and then you determine the type of hybridization. So for example, if in the central atom you have only 2 electron groups, those 2 electron groups will always be sp. That's it. Okay, and that is because the geometry is linear. All right, if you have 3 electron groups, then those 3 electron groups will always be trigonal planar, and that will give you hybrid orbitals of sp2, always, always. If you have 4 electron groups, now in the 4 electron groups, and even in the 3, you can have some that are bonding, some that are lone pairs, and it does not matter. So that's why we're looking only at the electron domains. We're not really looking at bonding electrons or non-bonding electrons. We're looking at the total number of electrons, okay, that you have on the central atom. So if you have 4 electron domains, then the hybridization will be sp3. And the geometry, now this is electron geometry, okay, this will be tetrahedral. This is not the shape of the molecule. Please remember that, okay, two different things. So the electron geometry will be tetrahedral. If you have 5, then it would be trigonal bipyramidal, which is sp3d. And if you have 6 electron groups, that's octahedral, and that's sp3d2. Okay, so this is how you would determine what the number of hybridized orbitals you will have in any kind of a molecule. These are the shapes that you will find for hybridized orbitals, and these are the ones that I stick to. I don't ask for F, as you know. We stick to the 5 main shapes, and our 5 main shapes are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Okay, and so the linear is always going to be sp, trigonal planar is going to be sp2, tetrahedral is going to be sp3, and so on and so forth. Now please remember, when we talk about tetrahedral and trigonal and all of this, this is electron geometry. This is not exactly the shape of the molecule. This is the shape of the hybridized orbitals. Okay, so whether you have lone pairs in there or they are bonding electrons, that doesn't matter. Okay, so it's the electron groups that matter, not the bonding and the non-bonding. So I gave you this table before also when we were talking about the VSEPR theory, and we went through the number of electron groups that you can have, the Axe formula related to that number of electron groups, the bond angles that are involved, okay, in that formula, some examples, and I gave you electron geometry and the shape of the molecule. Okay, now remember, the electron geometry and the shape may not be the same. Okay, so sometimes a tetrahedral is a tetrahedral, but sometimes a tetrahedral is a trigonal pyramidal, okay, because it has lone pair of electrons, all right? That's what ammonia has, and that is what is shown by the Axe formula. So in this table, I've also included the hybridization for you, okay? So if you have 2 electron groups, you will have sp hybridization. If you have 3, then you'll have sp2. So no matter what the shape of the molecule is, the hybridization is still going to be the same because you have 4 electron groups. Okay, so if you have the same number of electron groups, you have the same kind of hybridization. That is what I want to make sure that you understand from this table. Okay, so here if you have 5 electron groups, then all of them will have the same hybridization. All of them will have the same electron geometry, but the shape may not be the same. Okay, because the shape depends on how many atoms are actually connected to the central atom and how many lone pair of electrons you have. All right, and so that's what this table shows you over here. So let's look at a solved problem now for N2F4 dinitrogen tetrafluoride. Okay, so what we're going to look at is the bonding around the nitrogen atom. So the first thing that you do is you draw out the Lewis structure. So in the Lewis structure, we have nitrogen as the central atom. Now we have two central atoms here, okay, because it's two nitrogens. So we have two central atoms, and then the fluorine, which are 4. And then remember, as we talked about before in the previous chapter, you distribute them as symmetrically as possible, okay. And so nitrogen joins with nitrogen, and then of course the two fluorines go on either nitrogen. So this is what we get for our Lewis structure. Now to determine what the bonding is, okay, on the central atom, the valence bonding, okay, on the central atom, you take it step by step. So first of all, in the Lewis dot structure, what you see is that you have 3 bonding electrons and 1 non-bonding electron, okay, pair. So which means that there are 4 electron groups, okay, around the nitrogen. 4 electrons, and more accurately we can say AX3E. Okay, so you have 4 electron groups, 1, 2, 3, 4, 3 of which are bonding and 1 of them is lone pair. And that is not so critical at this point. The most important thing is that you have 4 electron groups, okay. So which means that if you have 4 electron groups, you have a tetrahedral arrangement. If you have a tetrahedral arrangement, then you have sp3 hybridized orbitals, and that's all there is to it, okay. And so both of the nitrogens are the same, and so which means that both of them are sp3 hybridized. Now for multiple bonds, okay, when you have multiple bonds, things are slightly different, not so different, okay, but we'll just go over it slightly with you. So if we have carbon dioxide molecule, in the case of carbon dioxide, carbon is the central atom and oxygen is the terminal atom. And this is what the Lewis structure was when we drew it out in the previous chapter. And so you have 2 double bonds, okay, with carbon. So carbon is sharing 2 electrons, okay, with 2 electrons of oxygen. So which means you have double bonds, okay, over here. So it means we have 2 electron groups. Now remember, each of these double bonds, they have 2 electrons each because there are 4 electrons being shared. However, when we look at the shape of the molecule, we look at each of these as a group of electrons. So here is a group of electron and here is a group of electrons, which means you have 2 groups of electrons. If you have 2 groups of electrons, then the hybridization will be sp. The electron geometry of this one is AX2 because you have the central atom of carbon A and then 2 of the atoms there is are X2. There are no lone pair of electrons left over. Okay, so which means that the hybridization on carbon is sp. Again, oxygen doesn't matter, it does not hybridize. Now look at HCN molecule, which is hydrogen cyanide, and here carbon is in the middle. Now carbon is sharing 1 electron with hydrogen and sharing 3 electrons with nitrogen, okay. And so carbon here is still the central atom, nitrogen is not the central atom here. So nitrogen is terminal, hydrogen is terminal. So we're focusing on carbon. Again, carbon has 2 electron groups, 1 electron group, 2 electron groups. And if you have 2 electron groups, then the hybridization is sp. That's it, okay. So as you can see that carbon can be really weird that way, okay, is because you can have different number of bonds, but you can still have the same hybridization. And where is that coming from? It's again coming from how many electron groups you have. That is what matters a lot when we look at hybridization, okay, not the number of bonds per se, but electron groups, okay, that you have around the central atom. So use that to determine what is going to be. So here is another problem for nitrate ion. Okay, and so let's look at the Lewis structure first for nitrate ion. And nitrate ion is nitrogen in the middle, and you have these 3 oxygens, okay, and O3 minus is the structure for nitrate ion. And then of course you have that 1 extra electron, and that extra electron goes to oxygen, okay, over here. So the number of electron groups on nitrogen is 1, 2, 3. That's it. There are no electrons left on nitrogen because one of the extra electrons has gone on oxygen. The other lone electron that was left is gone on oxygen as well. Okay, so nitrogen now has no electrons left over, and so nitrogen has 3 electron groups. If it has 3 electron groups, it's sp2. Okay, that is all there is to it. So these are all the things that we learned back in the other chapter with Lewis structures. So now we're getting a little bit deeper into hybridization. Okay, so which means that you can take almost any molecule and then you can determine what the hybridization would be on those. Let's look a little bit deeper into the hybridization of multiple bonds. In just a few slides before, we talked about carbon, as in carbon dioxide, and hydrogen cyanide, where carbon had a double bond, it was sp, and carbon had a triple bond, it was still sp. And then, of course, previously carbon was sp3 hybridized. So how does that work, where we have single bond, double bond, and triple bonds? How do the hybridizations work for those? And so single bonds are really quite easy to deal with. Okay, if you have diatomic molecules like hydrogen, then the overlap is an SS overlap. If you have a Cl2, a chlorine bond, then in chlorine, the last orbital that is overlapping is a P. So you have a very simple P overlap. And then in some cases, as we talked about before, in single bonds, you can also have hybridization. So in that hybridization, you have the sp, sp2, sp3 hybridized orbitals. And all of them so far, we have learned only about single bonds, okay, in the sp, sp2, sp3. All of those hybridized bonds, these are called sigma bonds. Okay, I didn't really specify the names before because now it's going to get a little bit different. So now I'm telling you that those are called sigma bonds, and that's how you differentiate between hybridized and unhybridized orbitals. Okay, so if you have unhybridized orbitals, like in hydrogen, you can just call them the SS bond. But as soon as you know they are hybridized, one way or another, whether it's sp, sp2, sp3, it doesn't matter. Those are called sigma bonds then. So when you have a double bond, then what happens? Okay, so in case of a double bond, we have a sigma bond and a pi bond. Okay, a pi bond comes from a p overlap. All right, and these are unhybridized p orbitals that are overlapping. In case of a triple bond, there is one sigma bond and two pi bonds. So the pi bond is just a p orbital overlap. All right, so in double bond, there is one pi bond. In a triple bond, there are two pi bonds and one sigma bond. Let's look at the structure ethylene. Okay, it's just CH2, CH2. The name is not so important. The structure is important. Okay, so by the time you draw the Lewis structure of ethylene, which is carbon joined with another carbon by a double bond. Okay, and so then you have the hydrogens, okay, on each of the carbon. Now, according to our way that we have worked before, carbon has 1, 2, 3 electron domains. So if you have 3 electron domains, then you have sp2 hybridization. The shape is going to be trigonal planar and the bond angle is going to be 120 degrees. Okay, and that is how we have learned, and that is the fact. Okay, that does not change at all. So what we know is that the hybridization on the central carbon is sp2. Okay, that is definitely happening. The other carbon is exactly the same as this carbon, so which means that this has also got 3 electron groups, and therefore it is also sp2. All right, so which means that we now need to look at what the hybridization looks at for all of this. Now, in case of hybridization, remember we talked about the excited state where carbon goes to, 1 electron goes from S to the P. That still happens. Okay, that is still happening for carbon, but what is not happening now is an equal mixing of all orbitals. Okay, and so how we explain the formation of the double bond for carbon over here is that we say that one p electron is left behind and only 2 of the p orbitals are mixing with the s. Okay, because we know that the hybridization is sp2. So how do we explain that? Okay, so this is the only explanation that is possible, is that only 3 orbitals are mixing and one of them is going to be left behind. All right, so we have 3 of the sp2 orbitals and we have 1 of the p orbital that is actually left behind. So this is what the structure will look like. Okay, where you have carbon, another carbon, and the green ones, okay, where you have the 3 of the sp2. So these are the green hybridized orbitals now. The purple one that is left over, poor thing, all by itself. So the p orbital is hanging out just by itself right there. And then the hydrogen atoms, okay, which are the 1s1, which are now overlapping with the hybridized orbital. So the 3 hybridized orbitals that we have, 2 of them are being used to bond with hydrogen, and 1 of them is being used to bond with the other carbon. And then we have the p left over. Okay, the p orbital, which was unhybridized, that's left over. That p orbital will actually start to overlap with the one next to it. Okay, and so there is a neighboring effect going on here, and that overlap ends up giving this kind of a bond. And this is not two bonds, by the way, it's the same orbital. And remember, in one orbital overlap you can only have two electrons, so essentially there are only two electrons over here. So here is the pi bond now, okay, the purple kind of a thing. All the other bonds here are sigma bonds because they are hybridized, whereas this bond here is now the pi bond because that is the unhybridized. And that is what happens in ethylene, okay, where you have a double bond. Let's look at acetylene now. In case of acetylene, we have C2H2, and you have two carbons, two hydrogens. By the time you draw the Lewis structure of this, you realize that carbon and carbon are joined together by a triple bond, and then you have the two hydrogens. Nice and symmetrical Lewis structure for acetylene. So here we have a triple bond on carbon. So we've dealt with carbon as a single bond, double bond, and now for carbon as a triple bond. The number of electron domains that we have on carbon is 2, and that is for each carbon. So in this central carbon, you have a hydrogen and the other carbon. For the second carbon, you have a carbon and a hydrogen. So we have 2 electron domains, which means that the hybridization is going to be sp, okay, coming from the 2 electron domains, which means that the shape is linear, bond angle is 180, and that is the characteristic of sp hybridization. So in this case, we have two central atoms, both of which are carbon, all right, which means, and we need to know that they're both carbon because we're going to draw the hybridized structure of this, okay? And so this is what the excited state looks like for carbon, again, just as before that we had. So if this is the excited state, now we're still forming sp hybridization. We're only going to mix two of the orbitals, one of the s and one of the p, okay, and then the two of the p will be left behind, all right, because we need one s and one p for the hybridization, and we know it is sp because the electron domains are 2, okay. Remember, there's nothing like a p hybridization, okay. All the p electrons are what we call degenerate, okay. So p is not going to hybridize by itself. When we talk about hybridization, it has to be between two different orbitals, okay. So sp hybridization. So one of the s and one of the p orbitals will now hybridize and give two sp hybridized orbitals, and the two p that did not hybridize are still hanging out there. So then this is what the structure will look like. All right, now we have the two carbons, okay, that are joined together by one of the hybridized orbital. The other hybridized orbital, sigma bond, is now bonded with hydrogen on either side. So that takes care of the two hybridized orbitals that we have. Okay, one hybridized electron here, one hybridized electron over here, all right? So which means that the two that are left over now are the p. Now remember, the p is dumbbell and they're both going in opposite or in different directions, okay? So this is one of the p, and here is the other p going in another direction, and the same thing goes for the other carbon because the other carbon also has the 2p left over, which are not hybridized. So again, there is a neighboring effect and you have this kind of an overlap going on, and now you form two pi bonds, okay, because you have one overlap here and one overlap for the other direction of the p orbital, okay. So now you have two pi bonds, so 2p left over, two pi bonds, and that's the characteristic of sp hybridization when you have a triple bond. Only when you have a triple bond, okay. So sp hybridization, when you had single bonds as in BeCl2, you did not see pi bonds because we didn't have any electrons left over. At that time, our p orbitals were empty, but now our p orbitals actually have electrons in them, all right, and that's what gives rise to the pi bonds. Let's look at a solved problem now for some of these structures. So the question is, how many pi bonds and sigma bonds do you have in each of the following molecules? So look at the first one, A, okay, which is CH2, Cl2. The number of electron groups that you have around the central carbon is 4. So then the hybridization should be sp3, because that is S, 1s and 3p. So there are 4. So that means we have 4 sigma bonds, okay, around the carbon. And 4 sigma bonds is coming from the fact that you have 4 single bonds, all right? So sp3 hybridization is 4 sigma bonds. Let's look at the next one over here. Carbon here has 3 electron groups, and the second carbon also has 3 electron groups. However, now this first carbon here has 2 single bonds and 1 double bond. So the 3 electron groups now are a little bit different. Okay, they're not quite the same, which means that you have sigma bonds as well as you have pi bonds because you have double bonds in there. Okay, and so the carbon bonds that we have here, the first carbon is sp2 hybridized, and the second carbon here is also sp2 hybridized, and only reason why they're sp2 hybridized is because they have a double bond, okay, in between. And so now we have 5 sigma bonds and 1 pi bond. Where are the 5 sigma bonds coming from? 1, 2, 3, 4, 5. Okay, and then the 1 pi bond is between the carbon-carbon. Okay, that's the double bond. Let's look at the last molecule, which really has a whole variety of bonds, okay, in here. So here we have the first carbon, which has 3 hydrogens attached to it, and the 3 hydrogens, if you spread them out, that would be 3 single bonds. Then here we have a carbon-carbon double bond, carbon-carbon single bond, but this carbon is still double bonded, okay, and then this carbon and this carbon are bonded by a triple bond. So we have a variety of carbons over here. So let's start with the first one. So if you have carbon with 3 hydrogens, meaning you have 3 single bonds, and then the 4th single bond is here. So this carbon must have 4 electron groups. 4 electron groups meaning you have sp3 hybridization. If you have carbon-carbon double bond, just like we had here previously, carbon-carbon double bond means that you have a double bond, which means that you have a pi bond. A pi bond means that you have sp2 hybridization. Because this carbon is sp2 hybridized, the other carbon also has to be sp2 hybridized in order to form the double bond. These two carbons then, they have 2 electron groups around them and a triple bond, which means that they are sp hybridized. Things are actually quite simple once you know some of the fundamentals, okay, of how to do things. So now we can write down all the different kinds of bonds we have in here, all right? And so we have 10 sigma bonds and 3 pi bonds. Where are the 3 pi bonds coming from? 1 from here and 2 from here. Okay, so they have a total of 3 pi bonds. The sigma bonds are 1, 2, 3, 3 from this carbon here, 4, 5, 6, 7, 8, 9, 10. Okay, so all the other bonds that are left over are all sigma bonds. And why are they sigma bonds? Because they are still hybridized. Okay, there are no bonds here that are not hybridized bonds. All of them are hybridized. So all of these molecules that we just did, all of them had hybridized bonds except for the pi bonds, okay, which are not hybridized. One of the last theories to talk about in bonding is molecular orbital theory. Whatever the Lewis theory and the valence bond theory cannot explain, the molecular orbital theory can explain. It's extremely theoretical and it's extremely exact. Okay, it tells you why anything can bond or not bond. All right, so it's really very accurate and explains a lot of phenomena that you would not normally understand. So first of all, what is MO theory? Again, MO theory is that atoms will approach each other for bonding, and so their atomic orbitals will overlap to form molecular orbitals, hence the name molecular orbital theory. Okay, so which means that by the time bonding is done, there are hardly any atomic orbitals left. Anything that is bonding would be molecular orbitals. That's one thing. And then the next is that if you have 2 atomic orbitals combining, then they will form 2 molecular orbitals, okay, which means that whatever number of atomic orbitals you are combining will give you the same number of molecular orbitals. So for example, if you had 4 atomic orbitals combining, they will give you 4 molecular orbitals. Okay, so you get equal number of molecular orbitals. Now half of those MOs are going to be bonding and half of them will be anti-bonding. So how are they combining and what is this bonding and anti-bonding stuff? The way the orbitals combine depends upon their energy and orientation. And the way I look at it is by wave function. So wave functions, if you remember, were waves, how electron moves, and they have positive regions and negative regions, okay, in them. So if you have the positive regions that are combining, those are called bonding. And if you have positive and negative regions combining, those are called anti-bonding. The way it is explained in your textbooks is that molecular orbitals that are concentrated in regions between the nuclei, which is the center of the orbital, are called bonding orbitals. Okay, and the only way you can find electrons concentrated in regions between them, okay, is when there is a high density of electrons. And the high density of electrons are only obtained if you have like types of wave functions. And then the molecular orbitals that have zero values, which means they have hardly anything in between the nuclei, which is then the center of the atomic orbital, those are called the antibonding orbitals, and they are usually formed by subtracting atomic orbitals. So bonding molecular orbitals are formed by adding, and the antibonding are formed by subtracting. The way I look at it is that when you have molecular orbitals and you form bonding orbitals, usually you have like kind of wave functions, and when you have antibonding, you have the opposite kinds, okay, and that's why you're subtracting. So you have positive and negative wave function. If you want to read more about this, then go to your PowerPoint and read on it on the ChemWiki, okay, it really explains it very well. So now I'm going to show you a diagram. And the way it works for hydrogen, and I'm taking hydrogen because it's a simple atom and a simple molecule, all right? So you have 1s1, 1s1 orbitals for both, and then you form a sigma bond, 1s2. Now in this case, we talk about sigma. We don't talk about the ss overlap. We are talking that as soon as you have an overlap, then you form a sigma bond. Okay, so in the previous part about the valence bond, we learned about the fact that you actually mix the orbitals to get sigma bonds, but now we're saying that any kind of an overlap will give you a sigma bond. So here we have the orbitals, okay, the 1s and the 1s of the hydrogen atoms. Now the hydrogen atoms, they're at the same energy level, okay, and so the electrons are starting off at the same energy level. But then when you combine them, which means that when they form hydrogen, then you'll end up forming two molecular orbitals. One molecular orbital is the sum, which is lower energy, and the other molecular orbital is higher in energy, and that is formed from the subtraction of these two orbitals. So the wave functions here should be positive, positive, or negative, negative, and there is a complete overlap going on. Whereas here you can see that the wave function is separated because the overlap is not possible. There's a node in the middle because the positive is separated from the negative. Okay, and that's why there's a difference. And that nodes creates the higher energy. You fill electrons in molecular orbital theory just like you would in Hund's rule of Bohr principle and Pauli exclusion principle, which means that you fill electrons from the lowest energy level. So which means that you fill out the electrons over here first, which is the lower energy level, which is the bonding orbitals. Okay, so you fill electrons here, which hydrogen has one electron each. Each of them is bringing one electron. So you put both the electrons over here, both will go here, both will go in opposite spin. The higher energy level one, the antibonding orbital, that is going to be empty then because it has no electrons left to fill. And it is also the case to show you that hydrogen will exist as H2 and not as H atoms, because at H atoms you will have really high energy, okay, in there. So hydrogen exists as H2 molecules. The only place where you find hydrogen atoms is actually in the sun, because that's where the energy is so high that hydrogen can exist as atoms. Okay, it has enough energy to have electrons in each of these orbitals. Otherwise, everywhere it should be H2. So the antibonding orbitals, those are called sigma star, or with an asterisk over here. Wherever you see a star, that means it's an antibonding higher energy level orbital, and then the bonding orbital is just designated as simple as it can be. And this should be 1s2 because now you have two electrons over here. But anyhow, these are still the s orbitals. The key points that I would like you to take away from this portion of bonding theory is that you should still understand the VSEPR model, because if you don't understand the VSEPR model, you will not understand the valence bond theory, okay? Because the valence bond theory incorporates the VSEPR model. Unless you know the shapes of molecules and the Lewis structures, you will not get to the valence bond theory. You should be able to identify different kinds of hybridization. You should be able to predict what the hybridization would be in different kinds of molecules, looking at the shape, looking at the structure, looking at the electron groups. You should be able to tell me the hybridization in multiple bonds, okay, as well. As far as the MO theory is concerned, I need you to just understand the concept of bonding and anti-bonding orbitals. Don't go too much into it yet. You will learn more about it as time goes on. Okay, so focus more on the valence bond theory, okay, and learn how to apply it.